Welcome to another tutorial in Ansys Workbench. In this tutorial, we're going to compute the Euler buckling load in a simple truss. The purpose of the tutorial is to demonstrate the process to compute the buckling loads in Ansys Workbench. We will also introduce joints and demonstrate how to insert a joint into a model. The truss we're going to model consists of two members that are pin connected together as shown. The top member is 2 meters long and is connected to the second member at the 1.5 meter mark. The second member is angled at 60 degrees from the vertical in a clockwise direction. All members are 6 centimeters in diameter and are made of structural steel. In modeling the boundary conditions, we will fix all three displacements at the left ends of the beams. We will also fix all of the rotations at these locations except for the Z rotation, which we will leave as free. To properly model the connection between the two beams, we will need to insert a joint. The joint will be able to translate and rotate in the global coordinate system. However, the translation in both beams at the connection point must be the same, and this condition will be provided by using a general joint. We want to compute the Euler buckling load in the diagonal member and compare that to the Ansys computed buckling load. To do the equation-based calculations, we first compute the length of the diagonal member, and it turns out to be 1.732 meters. We then sum moments about point A, and this will consist of two forces. The vertical component of the force at the joint, called R, and the applied 2,000-pound load at the end of the beam. The magnitude of R turns out to be 2,667 newtons. We then compute the axial load in the diagonal member. This load is FB and is computed to be 5,333 newtons. The critical buckling load is then computed to be 414,548 newtons. This load may seem high, but remember, this is assuming the load and the beam are perfectly aligned. We will now use Ansys to compute the critical buckling load in the diagonal member. To do this, we will build the geometry and space claim, and then use mechanical to develop the model. There are two parts to solving a buckling problem in Ansys. First, a static structural analysis must be performed. This analysis computes the loads in each member. Then the eigenvalue buckling solver is used to compute a load multiplier. The critical buckling load is computed by multiplying the load multiplier determined from the eigenvalue buckling solver by the load in the member determined from the static structural solution. So to begin, we will drag and drop a static structural solver and start space claim to build our geometry. After opening space claim, I'll right click, left click select new sketch plane, select the XY plane, click plan view, click on line to start drawing my lines, and I'll click on the center axis and drag a line 0 degrees, and I'll enter in 1,500 millimeters. Now I can middle scroll to zoom this in, control middle mouse button to move it to the center of the screen, zoom back in a little bit with the middle mouse roll. Now I can continue my line by hovering over the end of this line till I see the sphere, left click and drag it, and I'll drag this line 500 millimeters at an angle of 180 degrees and hit enter. Now I can come and draw my last line, click middle mouse button to move my structure, get my sphere, meaning I've selected the point, and now my angle here I know is 60 degrees from the vertical, so I will want to be 150 degrees from that angle, and I want my length to be 1,732 millimeters, so I will go ahead and click 1,732.0, enter, and I now have all the lines drawn on my structure. I'll hit escape twice, 3 times to back out of all the lines. Now I'll go to prepare, profiles, select a circular profile, come over to beam profiles, click on circle, right click, left click, edit beam profile, and now I can come and click on ruler dimension, click on the 10 millimeters and enter in the radius of this shaft or these beams, which will be 30 millimeters. So type 30, enter, and now I can scroll out. Now come back to design, and I have my structure. I can click on my structure tree. I can come up to my curves, and I can left click on the top one, shift left click the bottom one, come over to create, and those curves were now turned into beams. So I have my 3 beams, I have my beam profile, and now what I need to do is make sure that these top 2 beams are recognized as being one beam. So I will come and click on the top beam, highlights this member. I'll come to back up to design, then select, click on the top beam, highlights this member, control click the second beam, and now both of these members are selected. Now I will come over and right click and click move to new component. So I now have a new component, and I'll click on this component, and I'll come down to share topology and change that from none to merge. Now in my structure tree, I have a component that consists of 2 beams, which is essentially this top beam, and I have the second beam, which is this diagonal member down here, and my geometry has been created in space claim. I'm now ready to bring it into, so I will minimize my space claim window, double click on model to open mechanical. Once mechanical has opened, it appears as if my geometry has come in improperly, but I need to remember that this is an isometric view. I can come down here and click on the z-axis and look at it down the z-axis, and my truss looks like it should. I can check my geometry, and I have my top beam and I have my bottom angled beam. I can check my materials, and I have structural steel for both of them, and I have my cross section of a circle. I need to add a coordinate system because I'm going to put a joint here where these members come together. So coming to coordinate systems, I am going to open that up and right click on coordinate systems, click on insert coordinate system, and then I'll come down here and it says I need to click a geometry. So I'm going to come to this vertex and click that vertex, and then come over here and click apply, and you can see that this is located at 1.5 meters in X, 0 in Y, and 0 in Z. And so I now have a coordinate system here where I can put a joint. So coming to connections, I can click on connections, and I can see that there are no connections that have been automatically generated. I need to insert a joint where these 2 beams come together. So I will come over to connections and right click, insert, come over and scroll down to joint, click on joint, and now I come down to the details of the joint, and I can see that it is a body to body joint, which is what I want. If I click on here, I have the option to make it a body to ground, but I don't want to fix this body to the ground at that point, so I'll leave it as a body to body joint. I'll leave it as type general, so I'll scroll down, click on fixed, come down to general, and I'm going to put in a general joint. And now I'm going to leave the X, Y, and Z as fixed. This implies that the beams will be fixed together at that point. But instead of fixing the rotations as well, I'm going to click on the fix all, and then click again to free rotation in the Z along the Z axis. Now I'm ready to click the different parts of my structure. So I'm going to use this vertex as the scope, so I can come up to the vertex select that point, and now you can see that the point has been selected that exists on the top beam. So I can come over here and click on apply. Now I'll click this vertex again, but instead of clicking on the front plane, I'll click on this second plane and scroll down and enter this in as the mobile scope. And so I now have my coordinate system defined and my connection defined. I'm ready to go do my static structural. So I will come to static structural, and I will put on displacement boundary conditions. So I'll pick this vertex, control left click the second vertex, click apply. Two vertices have been selected, and I'm going to fix these in X, Y, and Z. And now I'm going to come over and do supports and type in a fixed rotation, and I will click these two vertices again and click apply. And on the rotation, I will leave it fixed in X, Y, but on the Z, I will go with a free rotation about the Z axis. So I now have a displacement and a rotation described. I'm ready to come up to loads, and I'm going to apply a force at the end of this beam. So I'll select this vertex. I'll come over to force, click apply, and I have one vertex. I will click the window to open up and change to components, and then the components will be 0 and X, and I'll enter a minus 2,000 newtons in the Y. So I'll now come to solution, click on solution, and I will want to look at the total deformation and possibly a directional deformation. I'll come down and change the orientation to the Y-axis on the directional deformation. And then I'll come over to Toolbox and enter in a beam tool. Now I have my loads applied, my boundary conditions applied. I have some output that I want to compute. I'll come up and hit solve. While it's solving, I'll click pause. So my solution has been obtained. I can come to my total deformation, and I can see that my tip has a large deformation. I can see that my middle member, top member here, bends a little bit. I can look at directional deformation, and then I can come down and open my beam tool and look at the maximum combined stresses and the minimum combined stresses. Now I'm ready to come back to, I can minimize these, and I'm ready to come back and look at the eigenvalue buckling problem. So I will minimize the mechanical window, and I will come back to eigenvalue buckling, left click on it, drag it over till my cursor is on top of model, and then I will let go, and this will introduce an eigenvalue buckling solver, and you can see that it automatically connects the engineering data, the geometry, and the model. So now when I come back to double click on model and I bring up my model, I can see that it has added this eigenvalue buckling module down here, and I'm ready to continue with that. We can see that there are several question marks in the eigenvalue buckling part of the project tree. The first one is with the pre-stress. It says none. I will left click on that, and then I'll come down here and I will click on this box and change it from none to static structural. And that's why we did the static structural solution, is so that we can compute this pre-stress. In terms of analysis settings, I'll click on analysis settings, and I'm going to look for 5 modes. These are the buckling modes that we talked about in class. So we'll look at the first 5 buckling modes of failure. The rest of these I can leave set as the default. Now I'll come to solution, and since I'm going to be looking at 5 buckling modes, I will look at the deformations for each of those modes, and so I will click on U and enter in total deformation, and I'll enter in 5 of those. And so now I can come to my first one, and it says mode 1, so I'll click on total deformation 2, and I need to change the mode number from 1 to 2. Then I will click on number 3 and change the mode to number 3. Click on 4 and change the mode to 4, and then click on 5 and change the mode to 5. I could also enter in a beam tool and other components, so I can come up to Toolbox, and you can see that everything here is grayed out in the drop down when we're in the fatigue module, but up here when we're in the regular solution, I have those values that I can look at in my beam tool. So I'm now ready to do a solution here and solve this, so I'll come up and click on solve, and I'll pause while it solves. One thing that I would point out is if you are highlighted on this part of the solution, which is the static structural solution, and click solve, it will just solve the static structural part of the problem. So in order to solve the eigenvalue buckling part, we need to click on solution here and then click solve. You can see I did that and I got a successful solution. At least I got the green checks. I can come and click on the first mode of buckling, and I can see that that mode is not one that I'm necessarily interested in. It's this long member here, buckling. The load multiplier is a negative number. If I look at the second deformation, again I get a negative number. My third deformation, I get another negative number and a mode of buckling that I'm not interested in. And now this is the buckling of the member that I'm interested in, and I see that I get a load multiplier of 78.125. So this is the load that I need to multiply by the force that is actually in this member in order to determine the critical buckling load. To determine the force in the member, I can come back up to my static structural solution, open my beam tool, click on direct stress, and now I can see the direct stress in this member here is given by 1.8878 e to the 6th. It's a negative, meaning it's in compression. So I can take this stress value, multiply it by the area of this member, and that will give me a load of 5,337, which is close to the load that I computed by hand. Then to get the overall critical buckling load of this member, I will take and come back down to this total deformation load multiplier of 78.125 or 152, and I will multiply that by the 5,337.6, and doing that I get a value of 417,146, which compares very close to the hand calculation results that I obtained. I hope you've enjoyed